This chapter will relate the concept of work and energy. We'll see that the work done by forces will be related to the variation of energy of the particle, and we'll learn how to solve problems in another way. Already we have developed kinetics and kinematics techniques to solve a certain problem. We'll be able to solve same problems but with different method that is sometime easier using this chapter. So in this chapter, we'll develop and apply the principle of work and energy that will involve force, velocity, and displacement. And we'll study also the relation between power and work. And we will include the idea also of efficiency of a system. In addition, we'll go over the concept of a conservative force and we'll apply the theorem of conservation of energy in order to solve kinetic problems. To start with, let us introduce what is the work of a force. Whenever you have a force applied on a body, this force will lead to displacement sometimes and sometimes no. So if you consider, for example, a table, you have a table on the ground. If you put a force, a vertical force on it, whatever is the force you do, you will not able to displace it. So you have a force, but you don't have a work. Because a work, the condition for a force to produce a work is that the force should have a component along displacement. Here, because you have the ground here, the ground will oppose any vertical displacement. So your only possible motion in this case will be to move parallel to the ground. And then to be able to cause a motion parallel to the ground, the force applied should have at least one component that is horizontal, and it can have a vertical component that will not do any work. This is why we say that in order to find the work of a force, we should first project this force. So we find its projection on the direction of motion. So let's say here, this is the component of the force along motion. And then we can calculate the work. And we say that the perpendicular component to motion will not contribute to the total work. From here, the definition of work. The elementary work for a small displacement ds, okay, the elementary work will be the projection of the force along ds. So as you can see here, this force is doing an angle of theta with displacement. So if I project the force along displacement, I get f cosine of theta. And then I multiply f cosine theta by the displacement ds. I get what is the elementary work done when I moved from this point to this one. Now, of course, if I want to get the total work for a certain displacement delta s, I should perform integration. So an integral procedure will be required if I have to move from a point S1 to S2. Now, if my force is constant and cosine theta is constant, then I can take them outside of the integral and say that the total work is f cosine theta times delta s. But this is not always the case, because sometimes the force is variable or the angle is variable. So if one of these two is varying, I should perform integration. Okay? Now, according to the definition of dot product, the dot product definition is in agreement with the work. Why? Because if you consider the displacement vector dr, if you consider the displacement vector dr and the force F, then if you do F dot product dr, by definition, when I do a dot product, I get the magnitude of the force times the magnitude of the second vector, which is dr, times cosine theta. which is the angle between the two vectors f and dr. And since we are taking a very small displacement, then dr segment is equal to the arc ds. So dr can be replaced by ds. And then this is in agreement with the definition of work. This is why we say we can find the work by just doing dot product of the force applied times the displacement vector. Any question on this? Eli, as I told you, 13.7 is not included in the program. It just posted for your own information, but we never, in the program, sometimes we just introduce the concept. In case you are interested, I can explain it for you, but it's not included in the program. So we never did examples on it or something like this, okay? So this is why you are just responsible until slide 48 that we covered together. And I told you already that I don't have recordings on cylindrical parts for AUB. This is why I will try to search for other recordings in other universities. If I find something, because some students were not able to attend class, if I find these videos, I will post them for you. If not, for students who are not able to be in class last time, go over this part, and if you have any question, let me know. Welcome. Okay, so now, as we said, if you want to find the total work when going from position 1 to position 2, then we have to integrate to an integral procedure. So to do the integral procedure, we should all have f as a function of s. If f is varying, theta also can be varying, so then I should provide theta function of s. Or I can use a graphical method. You know that the integral of a function with respect to a certain variable represents the area limited between the curve and the axis of the variable. So here, if I represent f cosine theta function of s, I can say that the work produced by f when I displace from s1 to s2 is equal to this area here. Okay. So I can graphically determine this area in case it's a simple area, as we did before, if you remember, for cases of displacement, velocity, and acceleration. And then we can find what is the work done between points 1 and 2. Now, we'll start to find the expression of work of force for conventional forces, okay? One of the most common force is the work of a weight. So for the work of a weight, we just have to apply the formula and find how the weight will affect, in which conditions the weight will have a work, in which condition it will not have. And we'll come with a general expression that will allow us to find the work of weight in a simple way, okay? So now, what is the weight? The weight is a vertical force that is downward. So in general, if we take x, y, z, and y is the vertical direction, then we can express the weight as minus wj. According to the definition of work, the work of a force is obtained by integral f dot product displacement. So let us replace first the force by its expression. We are considering the work of weight, so F is minus Wj. Now what about dr, the displacement dr? Since I have a 3D motion, then my displacement vector dr can be decomposed into 3 components, one along I, one along j, one along k. So my vector displacement dr, when you see bold letter here, this means that it's a vector. You can also present it just by an arrow. So dr is dxi plus dyj plus dzk. And then we can replace the position vector by its expression. And now we just do development. Okay, you know that because of the definition of dot product, if you do I dot j, you will get 0. Why? Because by definition, the dot product is the magnitude of the first vector, which is 1 here, times the magnitude of the second vector. For j, it's 1 also, times
cosine 90.
cosine the angle in between. But since I and j are perpendicular, so it's cosine 90. This means that this will cancel out. Okay, this will cancel out, and I have that I dot j is 0. Similarly, I dot k is 0. And only if I have the vector dot product itself, I will get between I, j, k, I will get a result different than 0. So here, j dot I 0, j dot k 0. However, j dot j is what? What is the dot product of a
Plus
vector?
1.
Yeah, it's 1 because it's magnitude of j times magnitude of j times cosine 0, and cosine 0 is 1. So j dot j is 1. And then I can say that when I have the weight, I just care for the variation in y. I don't care if I change my position in x and z, because if I move in a horizontal plane, the weight is perpendicular to motion. And we said that a force perpendicular to motion cannot produce any work. It can only produce a work if it has a component along motion. Okay, so as you move in a horizontal plane, the weight will not do any work. And then here you have integral between y1 and y2 of minus w dy. Now, in the majority of application we consider that the variation in altitude is not very high, so we can treat the weight as a constant force. Okay, of course, if you have, for example, a satellite application and you are dealing with very high changes in y, then you cannot consider the weight as constant. In this case, they will provide you with the expression of w function of y. And if you remember, we already derived this when we considered the gravitational force. If you remember, we derived together the expression of the gravitational force, and we said that it depends on the distance between the center of the earth and the particle. So if you consider this is y, and this is the radius of the earth, in case you have very high changes in y, then you should express w function of y. And we did it together. We said that the weight is the gravitational constant times the mass of the earth times the mass of the particle over the radius of the earth plus y squared. So in case you have large variations in y, you can express w function of y and integrate this function. But because in majority of applications we have delta y, if you want, relatively small, which will not lead to a variation in the weight, we can consider it as constant and then take it outside of the integral. And we obtain that the work of the weight when going from a certain position 1 to another position 2 is equal to minus w delta y. And why we have the minus? Because if we do a small interpretation, if I go from 1 to 2, so if I move upward, okay, delta y is positive. And as I move upward and the weight is down, the weight will oppose my motion or will help my motion?
Oppose.
It will oppose it. And whenever a force opposes motion, it will do a negative work. Okay, this is why I can verify here that when I move up, the work of weight is negative. When I move down, the work will be positive because delta y will become negative. So please keep in mind this relation is developed for y-axis positive upward. Okay, if in a problem they give you y-axis positive downward, what will be the difference? What will be the
W
yeah,
into y2 minus 1.
exactly. So what you will get that the expression of the work will be different instead of minus W delta Y, it will be equal to plus W delta Y. Okay, so pay attention, please, for the frame. You have a condition here to use minus W delta Y, then you should have your y-axis upward. If your y-axis is downward, you use plus W delta Y. Okay? Anyway, if you go back to the relations, the only difference will be here. If y-axis is down, instead of having minus Wj, you will have plus Wj. And then you will have here plus W delta Y because y-axis is positive down. Okay? Any question on this part? Fine. Okay. Now, another force of interest that is widely also encountered is, let me check. Yeah, the y-axis should be specified from beginning, okay? It can be positive up, it can be positive down. If it's positive upward, then the expression of your weight is minus the expression of the work of your weight is minus W delta Y, okay? Because look, if you have y-axis upward, this means that when you move up, the work should give you a negative result because the weight will oppose it. So you will have that the expression of the weight when y is upward is minus W delta Y. However, if you take a y-axis from beginning, your y-axis is downward, okay? Then when you move, if you want up, okay, delta Y already will be negative in this system. This is why you don't have to put the minus here. If y is positive downward, the work of the weight will be just W delta Y. Because when delta Y is negative, this means I have an upward motion and the work will be negative. And when I move downward, delta Y will be positive, and then as expected, the work should give me a positive result. So here it should be plus W delta Y, while in the other convention, when you take Y positive up, the expression should be minus W delta Y. Okay? So now, concerning the work of a spring force, also we encounter a lot springs. Okay, so we should be familiar with what is the expression of the work of a spring force. For a spring, the force developed is K times delta L. You are already familiar with the spring force expression. It's depending on the stretching or compression of your spring, okay? So here we'll try to develop a general formula for the work of a spring force, okay? Now, we should always understand that first we should specify our system and then to determine the work of the force. So here, for example, what I mean by this, if you have a ball and a spring, okay, you can consider the action of the ball on the spring, and by action reaction, the action of the spring on the ball will be opposite. Okay, so if the spring is my system of interest here, if I want to find what is the work done on the spring, then I should illustrate the force done by the particle on the spring. Let's say I moved my particle towards the right. Then I am causing stretching of my spring in case it's starting, let's say, from the unstretched legs. Okay, so as I move to the right, I am causing increase in the stretching. Okay, so I can define here, I can consider the unstretched position corresponding to L0 as my origin for S. So I consider that S equals 0 at this position. And this means that the value of S will illustrate for me what will be equal to delta L. Because delta L represents what? Delta L is the stretching of the spring. It's equal to the legs of the spring minus the unstretched length L0. Okay, and if I count S from the unstretched position, then if I just do L minus L0, I will get S. Okay, so please pay attention. This is only if I take S at the unstretched position. Okay, I can take any origin for S. If I take the origin for S is here at the beginning of the spring, then what will be delta L? I can express delta L as a function of S. So this will be S, and this will be L0. And then delta L in the expression of the spring force will be S minus L0. Okay, so always pay attention for your origin of S. In case you considered the origin of S here, then delta L will be just equal to S. In case you change the position of your origin, you should follow your new position. Okay, so according to this figure, we'll consider that S equals 0 at the unstretched position. This is why we can say that the value of S is an indication of the stretching or compression of the spring. If S is positive, the spring is stretched. If S is negative, this means I am compressing the spring. Now, I am interested into finding what is the work done on the spring. So, whenever I stretch my spring, the spring will develop on me a force that is opposite to the stretching effect. So if you want the green force represent the force of the spring on the ball, okay, while the red part, the red vector, will represent the force of the ball on the spring. Okay, now here they are studying first the work on the spring. So the work done by the ball on the spring. If I want to study this expression, I just have to say, to determine what is the work done on the spring from a position 1, any position 1. So let's say I started from position 1 here, and I ended by position 2 here, and I want to get the total work from 1 to 2, then I should apply the formula, which is integral from S1 to S2 Fs ds. Now here, because the force is along displacement, okay, I don't have to do cosine theta because theta is 0. And you have the displacement to the right, and your spring force is also to the right. Because we are, if you consider in this figure, it's a stretching state. Okay. Now, because they are collinear, then we have cosine 0 is 1. So if we apply the dot product, the work from 1 to 2 is integral from S1 to S2 of K delta L times ds. And we said that because we considered the unstretched position corresponding to S equals 0, delta L is S. So this is the stretching of my spring. Okay, so now I have a function to integrate. It's a linear function. Of course, it is linear if K is constant. In the majority of cases, we deal with elastic springs. Whenever we say it's an elastic spring, this means that the stiffness is constant. In case it's not elastic, they should tell you what is K function of S. So in case we deal with other types of springs, non-elastic springs, then we should give, K can be given function of S, and then we do integration. But in normal cases, if they don't say anything, we consider it's an elastic spring. It's a linear spring, so we can just K will be constant, and we can take it outside the integral. And then what will be the function to integrate? So if you take K outside, we just have integral from S1 to S2 of S ds. And then the integral of S is S square over 2. And we are integrating S square over 2 between S1 and S2. So what will be the final result? The work on the spring. So keep in mind, this is the work on the spring because we considered the spring as our system. So it's equal to half k as 2 square minus half k as 1 square, whereas 2 represents stretching at state 2 of the spring, and S1 represents the stretching at state 1. Now, what if we have compression? We'll see together that it's the same expression. Nothing will change. Why? Because look, we said that force is K times S. When S is positive, so if you have tension, then K times S will be positive. And this will represent the tension force exerted on the spring. Okay? Now, what if S is negative? If S is negative, so if you compress, automatically K times S will become negative. So when I put the force of this on the spring, force on spring equal to Ks, this formula is working for tension and for compression. Because when I have tension, S is positive and my force is to the right. And when S is negative, I will be compressing my spring, and still the expression will be K times S because the negative sign will be within S. This is why if you have stretching or compression, this formula will work. So this is the general formula giving you the work on the spring. Okay, but in general, in the majority of problems, you don't care for the spring, you care for the ball. So in general, your system will be the ball. So in case you are interested in the ball, the only thing you should do to deduce what is the work. So if I want to deduce what is the work on the ball of the spring force on the ball, what do I have to do here? The only modification I should do on this expression is what?
Negative, because the
Exactly.
opposite.
I take the opposite. Why? Because by action reaction, the force of the spring on the ball will be opposite to the force of the ball on the spring. Okay, so now if I consider the ball as my system, I will just take the opposite force, which is minus K S ds. So this will lead to the work on ball is just minus half K delta L2 square plus half K delta L1 square. Okay, so these are two formulas that are widely used. So whenever you have weight or spring, you can just apply these relations. Okay, any question on this? Okay, now let us consider a small example. So if I consider the following example, you have a small cart and you are pushing it with your hand. You are applying on it a certain force F here or T. And you want to find what is the total work done on your system. So whenever we have a problem involving work of forces, then we should first draw the free body diagram. We draw the free body diagram, we determine all forces acting on the system, and then we calculate the work of each force and we do the summation. Okay. So to start with, we have the normal reaction. So normal is perpendicular to contact. This is the contact line. Okay. So normal is perpendicular to the contact between the wheels and the ground. And of course, we have normal at both wheels, but we can just get a resultant for both. So I can sum both, and I have the resultant force. Now, what are other forces acting on the cart? Of course, we have the weight of the cart, W. And we have the tension force applied on it. So in total, we have 3 forces. In case we have in case we have a smooth surface, okay, no friction. So here they didn't mention anything. Because they didn't mention anything, this means that we have a smooth surface and no friction. In case we have a rough surface, they should give us the friction coefficient. Okay. So now, what we should do then is to consider each force separately and determine its work. Let us start with the normal. Can you tell me what is the work of the normal force here?
Zero.
Yes, very good. Because motion is along this line and the normal is perpendicular to motion. This means that it cannot produce any work. Okay, so first I can say that the work of N is equal to 0 because N is perpendicular to motion. Okay, now what are the other forces acting on the system? We have the weight, we have the tension. Now, for the weight, you have two options here to get the work of weight. You can use the formula we developed together, or you can use the conventional way. And you can say, let me do both. First, you can say it's a normal force. Let me project it along motion and then multiply by the displacement. So you can say that your weight here, your weight is vertical, okay? And therefore, it's not perpendicular to motion. So it has two components, one perpendicular to motion, one parallel to motion. This is the line of action of the weight. It's a vertical line. Now, how to determine what is the component perpendicular to motion, what is the component parallel to motion? We should find what is the angle between the direction of motion and the weight. And to do this, all we have to do is to look at our figure. And we know that the inclination angle is given. So the slope of your line is theta, it's given. And since the inclined is doing theta with the horizontal, this means that the angle between weight and the incline is 90 minus theta. And therefore, the angle between the weight and the perpendicular to motion will be theta, will be equal to theta. Okay, so now if you want to project W along the line of motion, which is the incline, you should multiply or by cosine 90 minus theta or by sine theta. Okay, and if you look at your figure, your car is moving up and the projection of the weight will be down. So the work of the weight will be positive or negative?
Negative.
Negative. So you can say from the first method of projection that the work of the weight is equal to minus W sine theta times the displacement S. Okay? S is the upward displacement here. It's the distance you are moving with. Okay, now let us try to use the other method we developed together. We developed together a method saying that if I take a y-axis upward, like this, then for this axis, relative to this axis, the expression of the weight is minus W delta y. Let me check that I will get exactly the same result using both methods. Because what is happening here? I'm not moving only along y, I'm moving along s. So this is my, if you want, I have, this is an s coordinate like this. And I want to try to find a relation between the displacement along s and the displacement along y. To do this, it's very simple. I just have to do a small figure. I say, let's say I have a displacement s, or delta s if you want, and we can take that the initial position at the origin. So delta s is equal to s. Then this delta S can be decomposed into two components, one in the horizontal direction, which is delta X, and one in the vertical direction, which is delta Y. So this is delta X and this is delta Y. And since we know the inclination angle theta, from this figure we can relate delta S to delta Y. Okay, so we can say that delta Y can be replaced by delta S sine theta. Okay, so then if I replace back delta Y by delta S sine theta, and delta S is S, because I considered that I started from the origin, then I obtained exactly the same expression, which is minus W sine theta times S. Okay, so I still have to determine the work of force T. So force T here is the only one doing a positive work, and it will create motion because it's pulling the projection of T on the direction of motion is positive. Okay, now because T is not along motion, I should also decompose it. I will decompose it into two components. All I need to know is the angle it's forming, and the angle is given. They told me that T is doing with the direction of motion, which is the incline, an angle of phi. So then I will say T will be decomposed into two components, one along motion and one perpendicular to motion. The component along motion is the one which will produce work and is equal to T cosine phi, while the component perpendicular to motion will not produce any work. So this is T sine phi will not produce any work, and this is the component along motion T cosine phi, which will produce work. And then I can say because the projection of T on the direction of motion is along the positive direction, so it's a positive work. And I have plus T cosine this angle times S. Okay? Any question on this? Okay. So let us start to do problems. We'll start with this problem. The 10-kilogram block rests on a smooth incline. If the spring is originally stretched 0.5 meters, determine the total work done by all forces